gentlemen. I must not have been in my good health, I believe, when I said that I would present a review of the 5th workshop on electrode phenomena here at your conference. I found out at the conference, of course, at the workshop, I said, well, all send me short versions of your contributions, and then I will all put them together, and we will have a nice review. I got all these short informations, they were that big, and I despaired. It became quite clear that this is not possible, and I think anyone who doubts this should consider he would be asked to give a review of this conference even after the first morning session here, or at the end of the conference within 30 minutes, or I believe I have a little bit more now, 40 minutes, so that is not something one can do. I tried to help the situation by changing the title of this lecture into Review of Present Understanding of Electrode Phenomena, and I didn't like that either because it implies some kind of a claim that one really would have the complete overview, the view of the whole matter. So what I will do here is an attempt, and it must be subjective. It can't be objective. I will tell you what I found was a highlight or some kind of chosen topic during the Electrode conference. So it is a personal view. And unfortunately, some of the people who were at the Electrode conference are sitting down here in the audience. And if they feel that I am quoting them completely incorrectly, they shouldn't blow their head, but just suffer with me. It is impossible to do justice to scientific workers. They always see their own work in a completely different light. I will try, at any rate. So, I have said it's a review after, not of. I'm not going to give a p-counting report of the Electrode workshop, mainly because it's not possible. I will pick those topics which I felt came out in the discussions and were particularly considered. The workshop was the 5th workshop on electrode phenomena in Berlin from the 24th to the 27th of May. And it was sponsored by the Academy of Science and the Physical Society of the GDR. I should mention here, I should have put that in writing, that we are particularly grateful to the enthusiastic work the local committee has done, Dr. Hansche, Dr. Jüttner, Dr. Wolf, and others. I will subdivide my talk into 3 sections. One will consider the workshop, and I will try to give you some statements about what has been discussed. Cathode phenomena have been discussed, including breakdown and arc ignition. Anode phenomena have been discussed, and unipolar arcs. Then I will make some more personal statement, what I think could be a classification at the cathode. And then I will look into the future, if time is left, what I feel would be an interesting topic for future investigations. So, let us start with the workshop. The idea of the workshop occurred on a flight from Boston to Europe to Dr. Delcroix and myself. We felt that the people working on electrode phenomena, whether in gases or in vacuum, doesn't matter, deserved some kind of a meeting where they could exchange their views. We felt that people working in industry and people working in scientific institutions of the universities had not sufficient contact, and particularly those people working on fusion seemed not to take any notice of, or little notice of what was going on in the other areas, and so work was repeated, was duplicated, and we thought we should have some kind of a conference first. And the first conference was in 1972 in Paris, and then there was one in 74 in Bucharest, in 76 in Estoril in Portugal, and in 78 in Bad Honnef in Germany, and in 80 it was supposed to be in Moscow. Due to some unfortunate developments, that didn't work out, and 82, the fifth one, was in Berlin, as I said. During the time of these workshops, it turned out that the people, you know, this develops its own dynamics, something like that. And it turned out that there was a growing interest in discussion and less interest in presentations. So gradually it formed into a workshop, and I think it was in Honnef where we really achieved the situation that we had lots of discussions. This is a very old building, some kind of a castle there in Honnef, and you can't leave, you have no distractions, and you are sitting together all day, and so you can't escape each other, and there was lots of discussions there. And in Berlin, we also tried that. We had review lectures in the morning and short contributions in the afternoon, but shorter contributions than here, and more discussion, although some of the people, particularly some of the Russian friends, felt that there should have been even more discussion. We had chosen Berlin intentionally because we felt it gets more of our friends from the East to the conference, and we were very successful with that. Most of the well-known scientists from Russia were present, like, for instance, Mesiac, Lyubimov, Rachovsky, Proskorovsky, Petrov, Sukova. I can't name them all here. This was very well attended from this side. So we had 4 days of morning review lectures, so I'm going to review here the review lectures, which already shows that it will not be easy. The object which I'm going to consider is shown on the next slide, please. That's not the object. I was careful. I went upstairs and have some other. If you don't work, I'm going to take something else here. Yeah, that's what I thought. Yeah. Well, that causes a little bit of a difficulty. They don't work? I thought they were normal size, but they're probably not too tall, they are too fat, probably, if it is European size. Well, since I was afraid that would happen, I ran out a moment ago. Oh, there it is. Oh, very good. Very good, very good. Thank you very much. So this is the object of the conference, and I want you to understand that this is not some kind of a painting which I am presenting. This is an honest photograph. This is a scanning electron microscope photograph by Little and Whitney 20 years ago, and the base of this protrusion here is of the order of 1 millimeter. And just to complete the picture, all I did was to write these words here. That is what the experimentalist finds and uses, and that is what the theoretician at least would like to have. There are very few theoreticians which use something different down here. And thank you for the slide. You can already try to prepare. No, the next one is not yet used. Step back here. So, the outstanding topics, which particularly were also very much discussed, was, for instance, the phenomenon of, at the cathode. I'm first talking about the cathode now. The phenomenon of explosive electron emission. Since you had this morning the lecture by the outstanding expert in the field, by Dr. Mesiac, I don't have to go very much into the details. I remember that Mesiac presented an analysis of these phenomena on the basis of 3 laws, one giving the relation between the current density and the relaxation time for the flare, one giving the space charge limited current, and one the constant velocity for the expansion of the flare, and with that he could explain some of these data of this really extreme phenomena. As you remember, we have nanosecond time developments, we have fields of 10 to 7 volt per centimeter, we have densities of 10 to 20 per centimeter cube, and so on. So that is really a situation difficult to describe. Dr. Messias also talked about the motion of the cloud over the surface. You heard this morning, so I'm embarrassed to give a not so excellent presentation here. The motion of the cloud over the surface. One of the essential points which I would like to stress is that he really could show that the reignitions occur, and that the reignitions occur not uniformly over the surface. There are reignitions in the environment of the original spot. Then there's an area where you have no craters, and then outside you have craters formed again. By the way, a phenomenon which also has been considered by Lyubimov and Rachowski. I will come back to this. Apart from Dr. Messias, Dr. Fursey gave interesting information about the reformation of protrusions on the surface, the current dependencies of subsequent pulses. It is impossible to give you details here about these findings, all these findings. There was one feature which particularly impressed me with respect to the last slide which you saw. You all know that if you talk to a theoretician, you say, well, what kind of crazy surface are you using? Such a flat, straight, plane surface is nothing which happens in realities. And theoreticians like to say, yeah, but remember, it is molten, the surface. And a molten surface, of course, is, I have a smooth surface and no tips. But 50 years ago, I think in 35, Louis Tonks already said that the field will cause protrusions. But I, as a theoretician, had never seen something like that. And first he showed a picture which I would like to show you too, because it impressed me very much. It's not by Fursey, but it is a picture which has been published in '81 by Porosky and Gabovich in a Russian journal. And it shows the surface of a molten copper surface, which has been molten by a hydrogen beam, and then shock frozen, and it was under the influence of 10 to 5 volt per centimeter field. Then it was shock frozen, and with a scanning microscope the photograph was taken, and there you can see that the usual excuse, we have a liquid surface, means very little, because this is even worse than the other picture which you saw. That's a picture which, besides many other things, first they showed on the conference. Thank you. Well, in the discussions, I want not only to report to you about the lectures, I want also to report about the discussions, because there sometimes it gets really nice and hot. I remember here about the explosive electron emission, the discussion got quite hot. And always when it got hot, the Russians start to talk in Russian with each other. I'm allowed to say this myself. Dr. Messias and we were standing at the side and didn't really get it because they were so engaged there. One feature in the discussion was brought up by Rachowski, who claimed that the current densities, Messias claims, 10 to 8, and Jüttner does, 10 to 8 m per centimeter square, could not possibly exist because they would require they would require much higher voltages than we measure. Rachowski and Lyubimov did a simple calculation, and they claimed to show that they need 100 or 200 or even more volts per voltage drop to get such high current densities. I personally don't believe that the calculation is correct, because they are using a simple conductivity model for the calculation, and they should include other transport phenomena like diffusion or thermal diffusion and other things. Yes? Yes? Yeah, I'm stepping on this always, that's the problem.
Let's see, let's try it right here. Maybe that'll...
Yes, that's very nice. Thank you very much. I will try to handle it better. So that was one point of the discussion. Another point of discussion was, if you have an explosive phenomena, what does really happen? For instance, during the initial, very initial phase, and that was what my questions this morning to Dr. Messias related to. During this very initial stage, the Nottingham heating is an important feature. The question is, in what parts of the tip which you are calculating, like Mitterauer did, do you produce a Nottingham heat? What is the spatial distribution within the tip? Another question was, what is the effect of having a whole solid part of the solid transforming into a vapor, and is there a continuous transition rather than a discontinuous surface? All the calculations speak about a discontinuous surface, but actually there's a continuous transition. You may have the so-called IF emission, which would change the picture. Another question was, what is explosive emission? Do you have first the transition from a solid state to a neutral vapor and then an ionization? Or do you have the transition from a solid state to a supercritical plasma and then an expansion? I did not get the final answers there, but that may have been my fault. I may not have gotten all the information there, but the final answer, I have scheduled to talk with Dr. Messias tomorrow, and maybe then I will understand it. So there was a lot of discussion about these things here, and the topic was very interesting. So I think I have to go a little bit faster. Another topic which had been discussed was crater formation. There was a paper by Juttner who provided a large amount of information about craters. I will try to summarize that very briefly. He is sitting here, and I hope it's what he wants to say, what he would say if he was here. For arcs up to 1 on a clean surface, he distinguishes between clean surface and contaminated surface. For arcs up to 100 amp, he claims that there will be only 1 or 2 spots, and that the spots move from the crater to the rim and to the next rim and to the next rim by steps. And that the time development for the craters is very short. That was one of his important statements, about 10 to minus 8 seconds. And that the crater formation depends on the temperature of the surface. I will show you the next slide, and there you can see, these are pictures which Dr. Juttner provided, fortunately, and these are molybdenum surfaces. This is on 1650 Kelvin degrees, and this on 300 Kelvin degrees, and the length is indicated at the side here. Both are clean surfaces, and you can see there's a difference in the structure of the autograph on the surface. Thank you. And with contamination, he found a completely different behavior. The craters, there's not only 1 crater or 2, but many craters, and I will come back to that when I talk about this topic down here. There was also one of the important conclusions was that Dr. Juttner said he felt that ion bombardment heating must be the decisive process in the formation of the crater because it is so fast. There was another contribution by Dr. Daalder, who is also very much interested in craters, and he showed from the observation of the random walk of the spots that they observe a Rayleigh law after some time, and from this Rayleigh law he could calculate the average step length and the development time. He came up with a step length of 3 crater diameters and development times of 10 to minus 6 to 10 to minus 10 seconds. These contributions also were discussed quite a bit, and one of the points in the discussion was the question whether joule heating and ion bombardment heating is dominating. One of the outstanding points was that Daalder said he had observed droplets from craters, the volume of the droplet being much larger than the crater. And yeah, that was a reaction of most of the people there. Some people said, is mass conservation not true anymore? But we finally settled that this might be possible because if you start to form the droplet from a mountain, from a protrusion, from some kind of a protrusion, then of course the mountain is also the material that may be larger than the crater itself, the crater volume. I have to hurry. Surface contaminations, how much time do I have, Professor? Surface contaminations, there were contributions of Dr. Juttner. Halfway through, fine. There were contributions, many more contributions, but some of the most important ones, again by Juttner, by Dr. Geil, by Lebimov, and Rachowski. The last one was a theoretical one. Juttner, as I already stated, found that he has a completely different structure on contaminations. I think I would like to have the last slide again, where a picture is shown of the crater structure on a contaminated surface with 10 micrometer, not so, this is the very last of the whole talk. No, I mean the one before. The what? The preceding slide. Please. You will see that there are many much smaller craters on such a contaminated surface, and according to Juttner, they exist simultaneously. There, you see the picture here. This is on a contaminated surface of molybdenum with 10 micrometers, nanometers, yes, I think. 10 nanometers of thickness of the layer. And the difference in the structure is obvious. According to Juttner, thank you for the slide. According to Juttner, the spot is not moving anymore from rim to rim to rim, but now the motion is determined by the expansion of the cloud. The plasma cloud moving over the surface and then reigniting will determine the velocity with which this moves. Dr. Geil, there would be much more to say, but time is too short. Dr. Geil considered crater formations in arcs with a high pressure, with atmospheric pressure in air, and found a difference between he has contamination layers of 2.5 nanometers and larger than 10 nanometers. And he finds a remarkable difference in his observations depending on what the size is of these layers. In particular, he claims that for the thick layers, there are switching phenomena, filamentary channels developing in a thermal runaway process, because the conductivity of the oxide layer changes very much with temperature, so you get a instability and you get a filamentary discharge going down there. He also said that he can calculate the velocity, how they move, the spots move across the surface. He gets 10 to 4 centimeters per second. And he also claims that the heating below the contamination layer blows up the contamination layer and provides a part of the material lost from the surface. This was also a phenomenon studied theoretically by... I will keep it in my hand now. Studied theoretically by Lebimov and Rachowski. They considered a very first approach to the plasma cloud over a spot, and they calculated the potential variation across a spot and the evaporation of contaminated material from the surface due to the expansion of the actual cathode spot or cathode cell, whatever you want to call it. And they find that the voltage at the rim of the plasma cloud is 100 to 120 times what the voltage is in the center. And therefore they claim reignition occurs at the rim and not close to the center. This may be seen in connection with the experimental observations of Messier. And also their calculation of the mass loss from the surface, they claim, shows that a substantial part of the mass loss is due to the evaporation of these contamination components on the surface of the electrode. The discussion about the contaminations was not as focused as in the other points, so I'm not going to elaborate very detailed on this. Now I need one more hand. Thank you. Okay. Anode phenomena. The anode phenomena also took 1 day of discussion there and presentation. Many features have been reported. The review lecture was by Dr. Kimblin, well organized and very instructive. An additional lecture by Dr. Miller was very useful. And the outstanding feature was some kind of a classification of the phenomena which have been observed at the anode surface. And Dr. Kimblin distinguished diffuse modes at the surface, anode spots, anode activity, and anode foot point. And I say it in my simple words, anode diffuse mode is a discharge going completely diffused to the anode surface. Anode spot is a constricted, highly constricted mode with strong evaporation from the anode. Anode foot points, no, excuse me. Dr. Kimblin distinguished anode activity and concentrated anode modes. So concentrated anode mode is a mode where which is concentrated, not so far as a spot, but without any visual contribution activity of the anode. And the anode activity is a time-varying luminous activity on the surface of the anode. Dr. Miller, on the other hand, distinguished diffuse modes, anode spots. That makes you happy because it's the same thing. But he has so-called foot points, pattern, and sputtered modes. Sputtered modes where the anode contributes due to sputtering. I hope I'm quoting you halfway correctly. And foot points where there is such a concentrated form, and patterns where you have several. I have 2 slides which you can quickly show, please. This one you forget. No time for that. The next slide will show you one of the demonstrations of Kimblin, a demonstration of Kimblin which I had a little bit to redraw. Pressure of nitrogen is plotted here, gap length is plotted there. In this area you have diffuse anode spot modes. Here that's of course nonsense, that should be diffuse anode mode. We will throw out men who put that in here. At home, I mean. Diffuse anode mode, this here is anode spot region, and here is a transition region where you have the anode activity, which is to me not very much surprising, because whenever you have a transition from one mode to another mode, I don't know whether that is your interpretation, it's mine, then you can expect that you have non-stationary phenomena at the surface, and so I'm not surprised to have this anode activity in this region here. So that I think is a very valuable information, one of the many he had to give. And Miller showed some diagram, which is on the next slide, please, on which you will probably not recognize anymore, Dr. Miller. I put 2 of your slides together to save time, and now you certainly won't recognize it now. It should be turned around, thank you. The current is plotted down here, the gap lengths up there, and then you see regions where you have diffuse anode, anode spot, and in between the foot points. It's okay, thank you for the slide. In the discussion, I remember the question was raised whether the foot points of Dr. Miller and the concentrated mode of Dr. Kimblin were the same. I may misinterpret them, but I had not the feeling that they said yes, at least not very enthusiastically. Kimblin also gave some future research topics which he liked to be considered. He also stated under what conditions, what favors diffuse, what favors spot, what favors activity. He also gave some statement about future research. The anode fault should be measured in the diffuse mode. The ion fluxes, the ion energy should be measured in the anode spot region. The ionization region should be localized. The influence of the ambient gas. And he advocated spectroscopic data of the luminous regions. And it just occurs to me that I forgot to mention that there were many other contributions about cassette phenomena, which you will partly hear here. Of course, there were measurements about erosion losses in magnetic fields, and as a consequence, the famous retrograde motion, which you all know. There is, I just was in Canada and visited there's a new theory there by Dr. Drewy about retrograde motion. There is a theory already well known by Dr. Schrader, who will talk today, I think, after this lecture about retrograde motion. Dr. Harris will talk about retrograde motion, so you are not going to miss this. I therefore do not have to give it here. And as far as anode phenomena are concerned, there were additional features. One lecture I remember was by Schuacher, trying to consider the magnetic constriction before the onset of the anode spot instability. And Schelleken had experimental findings. In the discussion, there was hot discussion because Schelleken claimed he had electron temperature lower than the ion temperature and collision dominated. And that seemed to some people rather strange. I don't know what happened to this point. No final result was achieved there. So that was anode spot. I'm turning now to the unipolar arc. There was a review lecture, a very good review lecture by Dr. Wolf, who summarized all the data which were available, and I could say that the essence of his statement was, in post-discharge observations, nearly all fusion devices show traces of arc spots on the surface of the limiter or other walls, which resemble very much the arc spots you observe in our equipments. It is not sure that each experiment has such an arc spot, but they are there. They are particularly there during the build-up and the ramp-down periods, and they are also there when you have instabilities in your discharges. I may add here an experience which I had in Köln. When I visited Köln, my feeling is I'm not at all sure whether these are unipolar arcs observed in these fusion devices, or all of them. The reason is that it is a terrible mess if you look into what happens there. There was this highly interesting lecture by Dr. Klausing from Oak Ridge, who showed a film with 3,000 pictures per second about what happens at the limiter. If you have seen the film, you give up explaining, because everything is happening there. Pieces of the wall are moving away, and there are explosions, and instabilities occur, and anything can happen there. And it is not, in the discussion of these unipolar phenomena, it came out that it wasn't clear at all whether they are unipolar or bipolar arcs. They are induction phenomena. They may just as well be normal bipolar arcs going through the device. There was also a discussion about the original Thompson criterion, Robson and Thompson criterion, no, Robson and Toneman criterion, and the opinion was that it is neither sufficient nor necessary. It is not sufficient because it considers only one aspect, and it is not necessary because you do not have to have the internal EMF in the sheath. You can have it in the plasma. No time to go into the details with that. If you have points there, you can ask me in the discussion. Thank you very much. That's most kind. Okay, so far the report. What about a summary? I'm not going to give you a summary about the unipolar arc, because this is in such elementary and first state that one cannot give a summary. I'm not going to give you a summary about the anode phenomena, because I think the anode phenomena were so well summarized by Kimblin that as far as this goes, that it is not necessary. What I'm trying to do is I want to make a statement about the situation at the cathode surface. And my claim is one can understand on a clean cathode surface, one can understand the phenomena, qualitatively at least, by three modes. There exist three modes, which are called the M0 mode, the M1 mode, and the ME mode. And if you show the next slide, then I will show where these modes are situated. If I plot the current density down here, current density at the spot, and the temperature of the surface up here, then there is one mode with a moderate current density of 10 to 5 m per centimeter square at a copper cathode, and the temperature just above the boiling point, which is a sequence of regular spot development steps, as Juttner claims. You see it in his observations, without any explosive phenomena. This mode exists for most of the metals except tungsten and molybdenum. This is a theoretical result, by the way, not an experimental one. And there's another mode with a very high current density, according to the theory, up 10 to 8 to 10 to 9 m per centimeter square, which also has a sequence of regular spot developments, steps. If the velocity is larger than sigma divided by tau, where sigma is the diameter of the spot and tau is the time of the spot development, either the runaway thermal runaway time or the stationary time. What does that mean? If the velocity is faster than this, then the spot has no time to fully develop, and you cut off the runaway and you cut off the development of the spot. Then it does regular steps as observed by, for instance by Juttner, and it has regular behavior. And then the third one is the spot at the same area calculated, but now for a velocity which is smaller than sigma over tau. And in this case, the instability, the thermal runaway, would fully develop, and then it is not anymore this regular phenomenon, but rather an explosive phenomenon where the liquid is thrown out and the vapor is transformed to a plasma on an extremely high time scale, maybe even not in the solid state. If you can show the next slide. Thank you very much. Let's have first a look on this slide here, and for reasons of time, forget all this, and forget all this down here, and look only on this picture here and on these modes here. My claim is, if you have a smooth surface, here it would be a smooth surface, no surface variations or little surface variations over the diameter of the spot. If you have this situation, you have the mode M0, where you have low current density, regular build-up, neighboring step to a neighboring side rim in the time of residence, tau r. And you have also the possibility of the high current density mode, so that you observe these both modes for this homogeneous spot. The same thing is true for the homogeneous smooth spot with enhancement coefficients. If the irregularities are not as pronounced as you saw it on the picture of Little and Whitney, then you can take into account this surface variation by enhancement coefficients in the theory, and both of these features can be treated simultaneously. There will be a shift in the current density or in the temperature, but no qualitative difference. And you have these modes here if tau is larger than tau r. If tau is smaller than tau r, you still have the low current density mode, but you have in addition this explosive mode, and what I want to stress is you can have an explosive mode without a micro protrusion, according to the theory. You don't need, you can have a completely flat surface and you still can have an explosive behavior. If you have this situation where you have a micro protrusion, or many micro protrusions as far as you also would have the ME mode. Of course, this ME mode and this ME mode, although in principle identical, if you evaluate them, the numerical values, the quantitative values for current density and temperature may be different, but the basic background is the same. So, I repeat, for the cathode surface, I believe we will have only 3 modes to explain the phenomena which we observe. Thank you for that slide. And since the red light is on, I come to the prospect. What would we like to see, or what would I like to see done in the future about the cathode phenomena? I again refer to the statements of Kimblin as far as anode phenomena is concerned. I would say on clean surface modes, I would like to understand time development of the temperature with the consequences. There is no calculation and no real understanding of the temperature development behind the surface. In particular, if you have a thermal runaway. What happens there is not understood and will not be understood for some time because it's such a complicated phenomenon. Then the motion of the liquid material under the discharge pressure and crater formation. This is something which has not been done. It has been calculated what happens assuming that the liquid stays in place. But actually the ion bombardment, as many authors have stated, pushes the liquid out of the surface and forms a crater. And that is something which has not been taken into account in the theory which I showed here and which should be taken into account. The phase transition from the solid to the supercritical plasma, which is so decisive for the explosive phenomena, I would like to be better understood. And most important, the analysis of the anode side plasma from the cathodic ball to the anode surface. I believe Dr. Boxman is going to talk about this today. There is, and Dr. Harris did already some calculations about this, but there's a lot to be done to understand this part of the plasma, and I believe before we have to get better insight here before we understand mass loss and other things, we are able to calculate those. Contaminated surface modes, my impression was anything reliable under properly specified conditions would be very valuable. And the general trend change which I expect is that there's not so much result-oriented work. We know what is expected. Uncertainty allows us to produce it by a model. What I hope is that the models treated so far, the understanding treated so far, can be put together in one model. We have understanding of the one aspect, of the other aspect, experimentally and theoretically. And my hope is for the future that we can put that in one complete model which is able to describe one typical subject. I mean, we will never have a model which describes all contaminated surfaces with inclusions and clean surface at the same time, but a model which completely describes one experimental setup presented. If I go back and think to the times when Weitzel, Rompe, and Schön had their first looks on the cathodes of arcs and found the spot with the spotless arc and the arc with a spot and with multiple spots, and if I think of the theoretical, one-dimensional theoretical approaches at that time, I do not want you to get from my lecture the impression that nothing has been achieved. I hope you got the impression that a lot has been achieved. At least I believe that there has been a tremendous progress and that we are very close to a preliminary, I want to say, understanding of the phenomena occurring at cassettes. And I hope that all of you stay interested in this subject and topic, which I believe is very fascinating because of the extreme conditions which one finds there. Thank you very much for your patience.
Alan Watson, University of Windsor. Dr. Ecker, when you say there's two types of mode with that diagram with the current density there, and you said that one was explosive and one wasn't, do you mean by that that in a non-explosive mode you would have no Tannberg jet, or has the Tannberg jet got nothing to do?
In the calculation, the Tannberg jet is not taken into account. The velocity is a parameter in the calculation. It is assumed the spot moves with a certain velocity by steps from one side to the neighboring side, and then the calculation is done in an existence diagram method where the Tannberg jet does not enter. But the size of the existence area is such that no danger comes from